Ja.
Oh, nou. Kun je naast het voldoende is?
Als je er een beetje meer ik graag dat deze heel dicht geplakt wordt. En dat moet ik dan hier ook nog hier. Als je meer heeft, ik denk dat het wel.
Oké, ga nog nodig.
Ja. Want ik voel het aan. Mijn computer die gaat flikkeren.
Oh, ja,
hier.
Nee, dat is niet de bedoeling.
Dus hier. Zo is het goed.
Oké.
En nu moet je staat die aan? Oh, ja.
Oké.
Ja.
Als er nog iets is, dan.
Dus die staat gekoppeld met hal 3.
Als het goed is, zou het wel moeten. Als het goed is, zou het wel moeten. Ja, maar als het er niet is, we zijn sowieso gewoon servicepunt. Laat het gewoon even weten als er iets is. Ik zeg, laat het gewoon even weten als er nog iets is.
Oké,
als het niet werkt. Zo.
Ja. Okay, you can already go onto Socrative, so that will be already done. It's the same name of the room, still IMD. You said that your email that it
it's not possible to record the lectures, right?
Because
for example,
yeah,
does
they
not
can't.
work.
Yeah,
But
they are too.
as you are also streaming the lecture to the other room via Zoom, you can record the lecture.
Yeah, so Zoom, I'm recording through Zoom. I don't know how the quality is going to be. But it's not. There is copper link, but there is no Trajectories. So
No, but the lecture is recorded, so you can, in case you
it's
cannot.
not. Now I am.
Yeah.
The previous one weren't.
Yeah.
All right, so for the rest of the week, we're still in the section about really just introducing the topic. And today we'll spend some time with notations, with flow description, just getting used to the notation that we'll be using, and a little bit of, yes? The microphone is not working?
Very soft.
Is it better? Do you hear any difference? No? You hear me lower? Is it better? No? But it's coming through, right? Okay, hold on. Headset. Now, any better? No? A little bit too much, no? No, it wasn't too much? All right. It's like a lot to me, but okay. So we'll be discussing notation a little bit and just description of flow fields, so vector fields, just a few things like that. So I asked you to watch a quick video about the notation, and that's mostly such that you can go from one notation to the others. So depending on what your background is, you might be used to notation in mathematics or notations in Kundu or in engineering, or index notations, which are mostly used by the physics community. So who did not watch the movie? Great. So just a quick reminder. So if there is no bar, right? Or so of course when I'm writing, it's hard to do bold. I can't do bold. It's just impossible. So bold is represented by a bar. So when I'm writing, I always, if there is no bar or it's not bolded in an exam sheet, then that would be a scalar. If there is a bar or it's bolded and it's lowercase, then it's a vector field. If it's a capital letter and it's bolded, I would write a capital letter with 2 bars, and that is a tensor. I mean, this is a matrix. Yes? And then I discussed a little bit the reason why I'm using these notations, and the notations are because when you look at your notation, in the way I write them, then you know what the rank of tensor is. Because if you don't see any bars, then it's a rank 0 tensor, so it's a scalar. If you see 1 bar, then it's a vector or a vector field. It is defined everywhere in space. And if you see 2 bars, then it's a matrix. And so, for instance, a stress tensor would always be a symbol with 2 bars, usually a capital signal. A vector field will always be a symbol, lowercase, with 1 bar. That would be a vector field. Right now, of course, you'll see a lot of objects, including dot products or divergence field or gradient fields. So you can also, just by looking at a mathematical object I'm writing, what rank tensor this is, because you just have to count the numbers of bars and you start from the left. So here, for example, this is the gradient of a scalar field. Right? This is a scalar, there's no bar. So when you go from left to right, you count the bars, 1 bar, 0 bar, it's a rank 1 tensor, that will be a vector field. Right? This one here is the gradient of a vector field. So if you look, you have 1 bar, you have nothing in between, so +1, this is 2. So this is going to be a matrix, always. Okay, the one trick is you always have to watch for dots, because the dots mean minus. Right? So here, you'll get used to that, but this is how we write the divergence field. That would be mathematical notations, that would be the full notations here, of course. This is here. Index notation, this is how I will write divergence. So you have to think I have one bar, so this is 1, but now I see a dot, so it's minus. So 1 minus, this is also 1, it's 0. Therefore, you have a scalar field, and you know that the divergence of a vector field is a scalar. Right? The divergence of a vector is a scalar. So you're back to here a scalar. Same for all of these things. So here I have 2. This is a dyadic product. I have 1. I don't have a dot plus 1. So this is a rank 2 tensor. It's going to be a matrix. Yeah. All right. So hopefully you've seen the video. So just to check that we are all on the same page, let's go to Socrative. And I put my own handwriting so you recognize this. So here you have this. What is that? Is that a scalar field? Is that a vector field? Is that a matrix field or rank 2 tensor field? Or is that none of the above? It's the same, AFD. Yeah. So throughout the whole semester, it will always be AFD. Yeah. All right. I'll let a few of you connect. We'll have a few others, so some people may join as we go along. But let's see already. Once I do 20 students, I'll see. All right. We all have it right. This is a single bar. You see one bar. You count once. It's a rank 1 tensor. It's a vector field. Very good. All right, next. What do we do next? Why finish? Oh, here, sorry. All right, here. This is rho U. That would be, the distribution of momentum in your field. Rho would be your density times the velocity field. So you're multiplying the density field by the velocity field. What do you have? You have a scalar, a vector, a matrix, or none of the above. You have a vector field, huh? Yes. Rho has no bar. It's a scalar field. A scalar field times a vector field is a vector field. So you see now, you know this is a vector. Has 3 components in 3D, 2 in 2D. Okay, very good. Let's continue. Now, yeah, I just did that one, of course. So this is here. This is how we write a divergence field. All right, so let's see how we are doing. And then going to be a scalar, vector, or matrix. And we hit 60 on the watch. Let's go. Whoops, sorry. I clicked the wrong button. Show result. This is a scalar field. And this is not a vector field. Why? Because you have one bar. That will be the nabla sign, which for now you will know what this represents, a differential operator. It's the way from the gradient, or anyway, so this is a differential operator that's acting on vectors. But you have one bar and you have a dot. So it is 1 minus 1, 0. And the rank 0 tensor is a scalar. So this is a scalar field. Okay, this is mu, partial u, partial y. What is that? Is that a scalar field? Is that a vector field? Is that a matrix field? Is that none of the above? If you're not sure and you want to check with your neighbor, feel free to have some discussion going on. I see some people hesitating. All right, cast your final votes. So this is a component of the stress tensor. You recognize that this is a shear stress. But the way it's written, it is still a scalar field. Yes, very good. There is no bar, no nothing. This number is a part of the stress tensor. So it's just one number taken out of your stress matrix. But the way it's written, really, when you watch this, you know this is just a scalar because there's no bar. There are no bars. Okay, I think that was the last one. Oh no, there's one more. What would I would say this one is a bit difficult. So you don't, yeah, well, we'll see if you're able to get it. Is that a scalar field? Is that a vector field? Is that a matrix field? Is that none of the above? I'll tell you what this is. But just from the notation, at this point, if you don't recognize what it will, you'll see this later on in the class, what this thing is. All right, we have to reach 60. Okay, what do we have here? This is a vector field. Yes, you're getting better at this. All right, why? You just count the bars. Now you have 1, a dot, so minus. You have 1, so this is 0, and then you have nothing. You still have 1 plus 1. This is 1. So it's a rank 1 tensor, right? And what that represents is the divergence of a tensor field. This is UU. This one here is UU. This is a dyadic. Tensor. So this is a rank 2 tensor, and you're taking the divergence of a rank 2 tensor. That is a vector field. This is a rank 1 tensor. So it's going to be a vector field. Yeah. All right, just keep practicing these things to make sure, when I'm writing something, at least this has 3 components, or it has 1 component, this is a matrix. Huh? This confusion happens a lot, that it's even, doing exams and reading, and I realize as soon as that is unclear on whether he's writing actually a tensor component, so a scalar, or whether he's writing a matrix, and then you have, matrix that get multiplied by other matrices, or things that just don't make sense. So make sure this is clear. Okay, and we'll leave that for later. All right, so that was a little something about notations. Now let's continue to description of fluid motion. Okay, so how do we describe, with our notations, how do we describe the motion of fluids? Or how do we represent, actually, not really the motion, but how do we represent flow? So we are in this part 1, 4. So this is part 1, not 4. Representation and description of flow or fluid motion. And actually, so the easiest way, the one that we are that you've seen before, to represent a flow is, of course, when you have full knowledge of the velocity field. Right? So this is what you would want. Once you know what the entire velocity field is, then in principle you have all the information. But sometimes it's represented elsewhere. There's one thing which I briefly discussed. That was the end of the lecture when I thought I still had a lot of time, but I didn't. And that is, there are two important fields, and that is going to be the velocity field, and that is going to be the pressure field. So keep those two in mind, because we are just looking at incompressible fluid. We're not going to couple that with anything related to heat and energy. If you have the full compressible gas dynamics, then that would be coupled to density field and temperature field. But we're really just focusing on two things, and that will be the velocity field and the pressure. At some point, I'm going to write U, and you're going to know this is the velocity field, right? But at the beginning, at least, I will make sure this is a field by just saying that this vector U is really defined at any position. So this is the position vector, right? So you can define the velocity of the flow at any single point, and as a function of time, right? If we have, I'll say that later. So same for the pressure field. Right? The two important fields are the velocity field. This is velocity, and this is pressure. Yeah. So this is the position vector, and this is here time. So when the flow, so when you, I just want to make a little definition here, because this is going to come again often in the class. And this is one of the questions, together with when you first read the problems and you're trying to get out what are the important physical phenomena, the other thing that you really immediately want to think about is that a steady flow or is that an unsteady flow? So we'll introduce the definition here. A steady flow, you have a steady flow when your velocity field and your pressure field are independent on time, right? So another word for steady flow would be stationary. So steady, if you hear steady or stationary, those are equivalent. Now, right away, let me tell you, there's one confusion that students that have oftentimes is that they have this idea that steady flow means that there is no flow. No, steady flow means that the flow is not changing with time. When there is no flow, you would say that u is equal to 0. The velocity, there's no flow of velocity, there's no flow of fluid, and therefore u is equal to 0. That would be static. That is not steady. Okay? So this is a little warning. Steady, which means time independent, is different than static. What you mean, static means there is no flow, right? Or no flow means u is equal to 0. Yeah, those are two different things. Of course, a static flow is a steady flow, but that's not. This is not true. We have many steady flows which are very dynamic. Eh? Is that clear? That nuance? Yeah. Exactly. So we'll discuss that, but this is very good that you bring it up. So one student here in the class just brings up that the mathematical definition of a steady flow would be one where the partial, so mathematically, I was going to mention that later on, but that's okay. Mathematically, this means that the partial with respect to time is equal to 0. That's what it means steady. That means you're looking at a particular point, and you're looking at the time variation, and there is no time variation. Therefore, it's equal to 0. Yeah? Okay, so this is a steady flow, and an unsteady flow is, what is this? And an unsteady flow is, when u and p are dependent on time. So an unsteady flow, this is when u and p vary with time. So partial over partial, you cannot assume that partial over partial t of whatever you're looking at is not equal to 0. Yeah? Yes?
Should P also be a vector?
No, P is pressure. So the pressure, so this is a very good point. So you already see here the way I'm writing it. P, the pressure, is not a vector field. It's a scalar field. Pressure is a number which you define at every single point. It has no direction. Right? Actually, it becomes a force once we'll discuss that. But once you define the surface, then you know that P is going to act normal to the surface. But the direction is undefined when you think about the pressure field. Yeah? So no bars for P. All right, so let's take an example of what a vector field looks like. So this would be the first one. This here describes perhaps the simplest flow you can think about. Well, besides the full translation besides just a full translation, that represents a solid body rotation. Okay, so this is a solid body rotation. Right, think about a bath or a big aquarium of water which you put on a rotating table. You spin, you spin, you spin. You know that because the walls are spinning, at some point the water is going to be flat, and at some point, you're outside of the lamp and the water just turns as a solid. And there's no actually relative motion, so it's very boring. Because if you're outside, you say, okay, there is flow, there is no zero. The velocity field is not 0, but if you were sitting on the rotating table, then you will see, depending on the frame of reference that you're in, this could be a static place, because you're rotating with that, and you don't see any relative motion of the flow. Yeah? But if you're sitting outside, if you're not sitting on the rotating table, then you see a solid rotation. This is a vector field. This is a velocity field. Okay? So this is how representing your flow with a velocity field would look like at every single point in space. So say here, this is my origin. Let's say here I have, let me do another color. Say here I have a particular point. Right? At any given point, say here, this is one point. Let me call that point X. At any point here, you can see that there is a vector associated, that is this vector here, which represents the velocity. Right? So your velocity field means that you have a velocity vector at every single point, which could be different from the one next to it. Yeah. So that here, this here is your position vector. And for the solid body rotation, you might remember that the velocity field, again, I know that this is a steady field. If I'm assuming that omega is constant, the rotation rate is constant, and it's just a steady field, it's equal to the solid rotation. You write like omega cross product your position vector. Right? That's how you represent the rotation. Omega being your rotation vector. So omega here, usually here will be 0, 0, and then omega in the third dimension, in the one coming outside of the board or of the tablet. So what are the coordinates? Once you have your vector field, you can write the coordinates of this vector field, and the coordinates are in the x direction minus omega y, and in the y direction omega x, right? Where x and y are the components of your position vector. Let me write that here clearly. So x here is equal to x, y, or if you write, I can write a column vector x, y. Yeah, is that clear? This is in Cartesian coordinates. Now, in polar coordinates, just to go back to the video that you may have watched on rotation. So this is here in Cartesian coordinates. In polar coordinates, you can write the same vector, right, as a function of the position vector, but now the position vector, you would not give the position vector as a function of x and y, you would give it as r and theta, like the radial and angular position. So the theta would be this angle here, what you see here, and r would be the distance from the origin, right? And this vector would be given in a local base. So then you have to think what in the local base, you have your velocity vector here, right? And you have to look at its component in the radial direction and the component in the hoop direction, or the circumferential direction. Hoop and circumferential are synonymous. Yeah. So what is the component of this vector in the radial direction? It is the component of this velocity field in the radial direction is 0. Yeah. And the component in the hoop direction is the velocity is going to be omega times the distance to the origin. That's the solid body rotation. And the velocity increases linearly with the distance to the center of rotation. Yeah? I mean, those sort of representation of motion you've had in your bachelor's before. All right, so this is a solid body rotation. Of course, this is very boring, but there are other flows that I want you slowly to get used to. Let's see another flow. That would be the irrotational vortex. So the irrotational vortex will become an extremely familiar figure in the second semester, in the second sort of quarter, in the second part of the class. So the flow of an irrotational vortex looks like that. Put it here. All right. And there what you see is it's sort of, I mean, we could think of the inverse of a solid body rotation. The solid body rotation turns out that you only have that loss of viscosity, and the rotational vortex is the opposite, in that it's a flow that seems to be rotating, but when there is absolutely no viscosity. And we'll discuss that in the second photo. But here you can also describe the flow. So this would be the vector field, and let me give you the flow in polar coordinates. The flow in polar coordinates, your velocity u, field u, and I'm going to write as a function of r and theta. This is r and theta really represents your position vector, and we're assuming the flow is time independent, so I could put time that, let's say this is steady. I'm writing this in polar coordinates, so remember the first coordinate will be the component of the velocity field in the local radial direction, yeah? So what would that be in this case? Yes, 0 again, so here, this is x, this is my position vector x, right? So in, like this, x, in the radial direction, it's 0, and in the hoop direction, it's not 0. In the hoop direction, it is inversely proportional to r, so it decreases with the distance to the origin. And so usually we write it as gamma. Gamma we'll discuss later on, that is called the circulation, times 2 pi r. This here is an r. It's a small r, not a small gamma. All right, is that clear? Yeah, so the easiest way, if you have full knowledge of the flow, then you know what the velocity field is. Just to check your ability into changing from one notation to the other, if you go back to the practice here, there's a small question. What is the velocity field of an irrotational vortex in Cartesian coordinates? And so I give you 5 minutes. The tables are nicely sort of organized, and you can work a little bit in groups. You can try to do the change of variable, of course, but that was discussed how you do that in the video that you watched about polar and cylindrical coordinates, or you can try to work by elimination. Just say, it can be this one, it can be this one, it has to be that one. All right, I'll give you 5 minutes. So in Cartesian coordinates, also, again, just like last time, if one of you could keep an eye on your student chat on WhatsApp, if there is a question coming from elsewhere in this room that you relate it to. Yeah? Can someone do that? Who can do that? You will do that?
I think you probably did that. Yeah, I mean, I'll look up. I think we saw you get X.
All right, so we're near the time where I want to ask you a vote. It is a little gymnastics, and you want to be very proficient in that kind of gymnastics. All right. Ten more students casting a vote. All right. Let's see. Okay, it is divided, but the majority had it right. Let me go by elimination. So B and D, they're using polar coordinates. So you know this is not in Cartesian coordinates. Right? If you see R and beta, then this is not in Cartesian coordinates. So then you have to, it is one of the above, so G is not correct for the smart students that thought they would beat me on that. Sometimes it is the right answer, yeah, but sometimes it's not. Okay, so here, so we are left with this one, with A, C, E, and F. Okay, so I'm gonna exclude A and C. So clearly A, if you look at that, right, this here would be, this here you just take, yeah, how do you explain this? So this is, you know, you're rewriting precisely that here in with Cartesian notation instead of R. But it cannot be the Cartesian that cannot be right, because this here is the velocity vector here is projected onto the local polar base. Right? If you look at this vector here, if you zoom onto this vector, if I'm zooming in, it has a non-zero component on X, right? So it cannot be this one. Here, you're writing a vector that has nothing in the X direction and has only something in the Y direction. So it can be that, right? Then let's move on to this one. Here, you have gamma X, gamma Y. So just look. I'm just going to tell you why this is wrong by just going directly to what you've already seen here, right? If you look at this point, that was in the solid body rotation, you clearly see your vector is going this way, right? And that makes sense because if I'm in this quadrant, if you think about being in this quadrant, X and Y are positive. So it's easy to think about, because any vector, you know, any position vector here will have a positive X and a positive Y, yeah? So you see that in this quadrant, the component in the X direction is negative for the vector, and the component in the Y direction is positive. Yes, so you see here, actually that excludes already 2. It cannot be this one, because here the component in the X direction is positive and the component in the Y position is also positive. And same for these two, so the only possible answer was E. Yeah, now let me show you what this velocity field here would look like. Your velocity vector C, right, where you have a component in the X direction, which is proportional to X, and a component in the Y direction, which is proportional to Y. That would look like this, right? So here, if this is my origin, and at this point here, X, right? So this is here, my position vector. This is my position vector. This here is X, and that here is Y. And at this point, you define a vector which is proportional to X in the X direction and proportional to Y in the Y direction. Which direction is it pointing towards? Radially outwards. So this is going to have the exact same direction as this X vector. So your velocity with you then would be in this direction. So a velocity field that looks like some constant X, some constant Y, is going to be a velocity field which is always radially everywhere. Your velocity field is pointing radially outwards. Yeah? Is that clear? Are there any questions on that? No, sorry? Sorry? This one here? Here, so you have a velocity field. If you have a velocity field, right, where at every single location, right, your velocity vector is proportional to the position vector, and you see this at the position xy, this vector has a direction which is in the same direction as the vector xy itself. And so this is my position vector going this way, right? Then my velocity field at this point is going to point in the same direction. It's going to point radially outwards. Yeah? Okay, now the last thing that could be a little bit, where am I? Here, no, here. Is how big is the magnitude of the vector, right? So here you have to realize that if you're thinking about the norm of this vector, right, if you think about the magnitude of the vector, you see that the magnitude of the vector decreases linearly with the distance to the origin. Yes? Is that clear? You have a 1 over r. You have a 1 over r decay. Gamma is a constant. This is circulation. It's a constant. The only variable that you have, position variable, is r. So it's decaying radially outwards. And you see here, this is the only vector whose magnitude is going to decay radially outwards. Because if you think about every single component, it's going to be a y divided by a y squared, or a y divided by an r squared. And here's an x divided by an r squared. So if you think about how it's going to grow, it's going to be left with a 1 over r decay. Here it doesn't work because you have an x and a y, but you're dividing it by square root of x squared plus y squared, which is r. So you have something which is going to, the numerator is going to grow with r, but the denominator also grows with r. So you're left with something which doesn't grow with the magnitude of the vector is not going to really change with the distance to the origin. Yes?
Why do you add the 2 pi if gamma's already a constant?
The 2 pi is just there. Yeah, because of how we'll define it later, because how you will define the circulation. But you don't have to worry about this for now. Yeah, I could have written alpha, except that later on you will constantly see gamma divided by 2 pi. So just to be constant with what we'll see in 2 months or a month, I don't know how many months, 1 month and a half, something. I put the 2 pi there. Yeah. All right. Okay. Any questions on the? No. All right. So I'll continue. So here, so this is velocity vectors, vector fields. Of course, you can also represent, and that's usually how, if I have to really quickly represent flow, I'll just represent something which looks like lines. So there is one important object that is often used to represent flow, and those are streamlines. All right, and here is the definition of a streamline. So a streamline is, well, let me just give it an idea here. Here you have an instantaneous snapshot of the flow, and it doesn't change. The flow here is a steady flow. And then one way of representing this flow would be that you could just draw a line where at every single point, your line is tangent to the local velocity vector, right? And that gives you an idea of if the flow was steady, sometimes it is unsteady, but if the flow was steady, where would that material go if the flow was steady? This is called a streamline, but it's really related to the instantaneous flow field. So the streamline is a curve which is tangent, which at each point, I would say, which at each point is tangent to the local flow velocity vector. So I'm writing flow velocity that you remember. This is really, we're talking about a flow field, not a single particle, but eventually I'll just talk about the velocity field, and to the local flow velocity vector. Okay. So important to remember tangent and important to write the local flow velocity vector. Yeah, now I'm going to put a attention mark. This is an instantaneous snapshot of the velocity field. This is when you look when considering the flow field at a given time. So this is a snapshot or an instantaneous snapshot of the velocity field. Yeah. So let me show you how streamlines look like, and then we'll just quickly look this on MATLAB. So this is, for instance, the flow around a cylinder. You will see this flow many, many times in the second quarter. So you will see it once already. All right, so this is the vector field. The blue vector fields here represent the irrotational flow around the cylinder. This is a velocity field. Flow around a cylinder. Dimension, a planar flow. And so you see here those red lines at every single point. If you zoomed in, you can put arrows on it. If you zoomed in here, you see that at this point, the red curve is tangent to the local velocity field. Right? And if you zoomed in here, you kind of see, maybe I can zoom in, I don't know how much you see here, but you know, at this point, you see this blue vector here. Right, your red curve is tangent to this blue, to the local velocity field. Those are streamlines. Yeah? Okay, so I have a few more minutes. I'll show you that on a simple little animation. All right, so here. And what we'll do is we're just looking at a snapshot of a velocity field, but eventually the velocity field will change in time, so I'll show you that. All right, so here's my velocity field. Okay, so currently I'm just looking at arrows. So this is really just the velocity field. But of course, the velocity field might be unsteady. So here I'm trying to represent, like, bit by bit, an unsteady velocity field, which would correspond, don't think too much about the physics behind that, we'll discuss that in the second quarter, but it would correspond to a flow which is initially in front of a cylinder, and you start to rotate the cylinder, and because you rotate the cylinder, some of the flow is accelerated on one side and slow down on the other, right? And so here we're slowly imparting some rotation onto the cylinder, and in time, the flow velocity changes. So later on, we'll see some tableau. Later on, this is slow to respond, but you see later on, you see the flow is slightly accelerated on the top and slows down a little bit on the bottom. Do you see that? So eventually you have a flow field which has a higher magnitude on the top, so towards here, right? And you see my pointer? Yes, so here, and slightly higher here, and slightly lower there. So it is unsteady. The velocity field though is a snapshot. Every single one of these velocity vectors are plotted at the same time. Yes, they have snapshot views of the velocity field. This is how you can represent that. Of course, if you now want to represent the streamlines, then the streamlines, you're going to have a different streamline pattern for every single snapshot. All right, so here was the flow at the beginning, the flow on the cylinder, and you can represent the streamline. Again, the streamlines, one line is everywhere tangent to the local velocity vector at this one time. Yeah, but of course, later on, the streamline pattern changes. So at every single time, you have a streamline. So the streamline pattern is really an instantaneous snapshot of where the flow goes. Is that clear? Yes? That's what streamlines are. It is this time delivery. So I'll see you back in 15 minutes.
Still no questions. So very clear.
Oh, still no questions from them. Okay. Good.
One, two questions, right?
Yeah.
So now you create lift, right? I mean, it's
Yes.
no pressure
Well,
there.
this we'll discuss that. This is in the second quarter. Yeah. If you already know that.
I had a question about your one thing. You call this the outer product, right?
Outer
That's
product,
like,
yeah,
it
or
should be
a dyadic product.
a tensor.
It
But
is a tensor, yeah.
this is like also an outer product, right?
No, the cross doesn't change the order of the tensor.
Yeah, but so that's the problem in way of for me of understanding, because we call this out product.
No, but I call this a dyadic. This is a dyadic. This is a
But
dyadic
also
product.
call this like an outer product.
Yeah, but this is a cross product. I never call that an outer product.
Yeah,
This
no,
is a
but we
dyadic.
call this an out product in Dutch.
And what?
Out product in Dutch. So they make it for conducting. So I should just be very careful of that outer product. So it's not.
Yeah, usually I say dyadic product.
Yeah.
But I know some people call that the outer product, but usually dyadic. I call that the dyadic product.
And that is like.
Just take, yeah. It's just if you multiply this, if you want to think about in math, you would write a vector times the transpose of the other. It's just A. Think of A column vector. A would be a column vector, and B.
Yeah, or A transpose.
So,
Yeah.
so it gives you.
So this is with A1, B1, this is A and Bn, right?
Yeah, but you only have 3 components in my
Yeah,
case,
this
but
this time, yeah, okay.
Yeah.
So this is A1, B, yeah.
Yes. And so it's a rank 1. It's always a rank 1. I mean, the rank in terms of invertibility, you always only
and
have
this is
1
like,
non-zero eigenvalue.
Yeah, perpendicular on A and B, right?
This is a cross product.
Yeah. So the result is perpendicular on A and B.
Yeah. It's almost A and B.
Yes. So this difference, we never had this under this word in the back.
Dyadic product. Yeah. I don't know what. Yeah.
So and we call this out product.
Yeah.
To make it even more complicated.
Yeah. Okay, just give me 2 seconds. Yes.
For the one where it was proportional to x and y, you said that the graph would look like this, like the flow.
Yeah.
So the option that was right, how would that look? Where it's inversely proportional to x and.
Well, the inversely proportional.
Yeah, like
the magnitude means that your vector, the magnitude of your vector is going to get smaller as you move further away.
Okay.
Yeah. But I mean, you already know. We plotted it. Huh? This is. It looks like that. This is the thing that you presented.
Okay, but so
no, not this one. Sorry, this one. You presented that rotational vortex. So that's the vector field that we presented.
So basically, it would point this way in this coordinate because it's inversely proportional to x. Or?
No, that has nothing. The magnitude. See, there are 2 things. No. The magnitude means you're going to have something which is proportional to minus y x.
Yeah.
And then on top of that, this is divided by r squared, if you mean. So the magnitude is inversely proportional to r.
Okay.
So the size of your vectors becomes smaller and smaller as you move further away from the center of rotation, if you want, and it's pointing in the hook direction.
Okay. And x has a negative sign.
Why do you? Well, What,
No, no.
what do you mean? X
I mean, when we are converting him from polar to Cartesian for the irrotational flow.
I think you need to watch the video on
This
coordinates.
one. So there'll be the negatives. There'll be negative direction for the Cartesian coordinate in the
This
x.
is wrong. This is a y. You see, you already have it wrong.
Okay.
Yeah. Do watch the videos.
Okay.
This is something. It's not like, oh, this is gonna look like. You just need to do it once seriously yourself.
Okay.
Once you'll see, then you'll be fine.
All right.
Did you watch the video? Okay. Do it again.
Okay.
And if you still have questions, then we need to make sure you're able to do that.
Okay.
Yeah, because here this is wrong. Yeah, this is
Okay.
This is gamma minus gamma y and gamma x. But you have to see where it's coming from.
All right.
Yeah.
Okay.
So in the notation video, you said that A cross B and AB is the same.
No, sometimes people call, well, okay, then it's different.
That's why I really asked the question.
No, then if there is just a cross, then it's a cross product.
Yeah.
But you can represent the dyadic product with a cross and a circle around. This is where I didn't get the question. In mathematics, usually the outer product in mathematics, you present with a cross and a circle around.
Okay.
That is not a cross product.
Okay. Yeah. That makes it even more.
All right.
Okay. Yes. Thanks.
Okay. But this is if you're a mathematician. If you're not, then just forget about that. Yeah. Yes.
Quick question for the rotational vortex. You just said. So in polar coordinates, you said u r theta is 0 and this.
That means that you have 0 component. Think about the
I mean, for 0, it that means along the radius, so the velocity are uniform.
Well, it means that you have no component along the real direction. It means that this is the origin. And I'm looking at this point.
Yes.
And my vector, I know it's in the real direction. There's 0 component in the origin.
Okay, it's only on the point, not along the radius. Okay, yeah, because
No, it's only at this one point.
Yeah. Okay, I mean, yeah, because firstly, I think it's uniform along the radius, but it's not true because there is
It's not pressure difference, 0.
Yeah. Okay.
Okay, I got it. Yeah.
So for this question, we have to convert polar into Cartesian.
Yes, do it. If you're unclear, just do it. Because of course, this is you can
I
play
mean,
with
like, what is like the basic formula for the conversion of?
So there is a video online that you should watch it. If you're unclear about cylindrical, polar, and Cartesian coordinates, this is something that you've seen in your bachelor in principle, going from one coordinate system to the other. And if you're unclear, then you need to watch the video, make sure you're comfortable with that. All right, so we are going to start again. There's another theoretical clause. We discussed the streamlines that represent really an instantaneous snapshot of where the fluid is going, of the flow. but there is something else which sometimes might be of interest, and it's also of interest if you're thinking about, what is a fluid particle doing, what kind of acceleration you have in the flow, and these are particle path lines. But if you think about particle path lines, usually you think about an unsteady flow, because the particle path lines in a steady flow are just a streamline. If the flow doesn't change, then of course, if you think about a flow that doesn't change with time, then you'll see that the particle is going to follow the path, which is exactly the streamline. Does that make sense? Yeah. All right. So a particle path line, the definition of a particle path line is actually the physical trajectory that a material element of fluid would follow. Okay. So a particle path line. The particle path line is the actual or physical trajectory followed by material element of fluid. Right, and here the important term is a material element of fluid. And that we'll come back to this idea many times. And so I should add, so the particle path line is the physical trajectory followed by a material element, and we follow this material, the same material element over time, and that we follow over time. So that's what I'm representing here. Say, assume we have flow. Here I'm representing, I'm not telling you what these are. It could be streamlines or particle path lines, but just that is sort of a generic representation of flow, but think about an unsteady flow. Right? Think this flow here is changing with time. This is here unsteady. And you isolate a material particle. Right? That has, you want to think of it as having a certain number of molecules of water or whatever. Right? And then as you have flow, you're thinking, what is the trajectory of exactly this material element? It has mass, it has the molecule, where is that going? And so you follow, that's the concept of a material element. And the reason why it's important is because when you think about dynamics, you know that Newton's law, which is dynamics, applies to a certain mass, it applies to a material. So once we start writing Newton's law, the law that you already know, the for continuum, which dislocates and which is not as easy to represent mathematically as a solid object, we still need to be able to apply the same dynamics principle, and so we have to have this concept of material element. Is it clear to you what a material element is? So it's really you have this pack of material. And you're following where it's going. So it's being carried with, of course, the velocity. Yeah? Okay. So the way you can think about this is, let's say this is here my material particle, right? So I'm going to call this here, I'm going to give it a name, and this is now P. Not to be confused with the pressure field, I'm just calling my particle P. And therefore, if I follow this particle, right, I will have full knowledge of where it went if I know its position as a function of time. Now, this xp of t is really the position of this one particular particle, right? Not another particle. This is the one that I represented here. This is xp of t. Is that clear? So you have three components, x, y, and z, and they're all functions of time. And you can uniquely define your particle p if you know where it was at time 0. So let's say that we're gonna fix that. We're gonna say that xp at time equals 0 is equal to x naught. Let's say this position is x naught. That means that initially my particle was at this location at time equals 0, and now it's traveled somewhere else. It's somewhere here. Yeah, that's how you can define a particle trajectory. Okay, now you can go on to Socrates, and here is a question for you. So hold on. I forgot to mention one notation and that is the following. So you think about an unsteady flow, right? And your unsteady flow is given, of course, by the velocity field, which is a function of position, But now it's also a function of time, and time, you may change as a function of time. And with this here, once you have this, you have the full description of your flow field, of your velocity field. Right, so here, if you go on Socratic, I give you 5 minutes to answer this question. So here, same notations, and I'm asking you which one of these mathematical formulas, or whatever you want to call it, which one of these represent the velocity of your particle P at time t? Yeah? There can be more than one. If you find, you can, I think in principle it's multiple, you can click several of these. So that's the question. I give you 5 minutes. And so this is the time where you can be now. You can just work by table in the other room as well, in room 3. Just try to work also by elimination. Which notation makes sense, which notation does not make sense. So note that here I couldn't do boldface with Socrative. So this X here should be a boldface. There should be a line under this XP. There should be a line under this U. There should be a line under this XP. There should be a line under this small u. A line under this small u, this capital X, all of that. And there should be lines underneath. Those are XP. But the small XYZ here, there are no lines under. Those are just the X, Y, and Z components.
It's not a partial derivative. So I wrote a partial on A and I wrote the straight derivative on C. So that's the wrong notation. You have to take a partial on C. In order to add a partial, So, velocity is greater.
So we have quorum in terms of answers. Let's see. All right. It's mostly correct, you know, because of course there are two right answers, which are C and F. Everything which is in between is incorrect. Let me tell you why. So some people, the important thing is some people are hesitating between A and C. Right? Of course, it looks almost the same, and you can say, well, but it's important that you know what you're writing mathematically. If you have a function of a single variable, the only differential sort of operator which you know is a straight derivative. When you have a function of a single variable, this is the same, you know, operation that you know since high school. You differentiate with respect to your single variable. And the moment you write partials, that's because you're assuming they have a function of several variables. And so what you have to see here is that the moment you say, I'm following this particle, you identify the particle, then everything is only a function of time. Right? Your xp, capital XP, the position of the particle, is only a function of time. It's not a function of x, y, and z. X, y, and z are fixed because you have to follow now this trajectory. Yeah? So it's a function of a single variable, and therefore the velocity is just the derivative with respect to time of your particle position. This is really what we're writing here is really the definition of the velocity which you've seen since high school. Yeah, that's it, precisely that. Capital U was not even defined, so forget about this. A was not defined. Okay, now let's look at the other one. And that's looking at something. This is looking at what is the velocity really, what is it? This is sort of a mathematical definition, but knowing that the particle now has to follow the flow, what is the velocity? That would be F. That would be because the particle at any given time has to move with the flow velocity at the position at which it is at this given time. Mathematically, how do you write this? We write this, the velocity field u at the current location of the particle, which is xp, which is the function of t. Yeah? Here, this is too generic. You know, which x? This is just a regular velocity field. You haven't defined exactly where you're taking the velocity, so that's not correct. And this is essentially the same. And of course, ux not t. This is the velocity at a later time at the position where the particle was at time equals 0. So it's not that. Yeah? Is that clear? Okay, with that, actually, now you can already go back to here, and if you have ever, in one of the homeworks, we'll have to do that in the next homework, compute particle trajectories. So how do you compute particle trajectories? So to compute particle trajectories, you need to know, if you know the velocity field, and knowing your velocity field and knowing the position of your particle, your initial condition, so xp at time t, at t equals 0 is equal to x naught, for instance. Knowing that, how do you compute your particle trajectory? You have to solve a differential equation. So you have to solve an ordinary differential equation, because it's going to be a differential equation which involves the function of a single variable, where you essentially say, well, we just said, all right, what do you want to know? I want to know my particle position, right? But I don't have information directly about the particle position. I have information about the velocity of my particle. So the velocity of my particle, which is what we just wrote, dt of xp as a function of t, right? This is the definition of your particle velocity. You're saying that this particle, the velocity of my particle, has to be equal to what? To the flow velocity at the location of my particle at time t. So you have to say this is equal to the velocity at the location of my particle, which is xp of t at time t. This will give you an ODE, so an ordinary differential equation, and you have to solve it subject to your initial condition. Yeah? So there is one problem in the homework. I leave it from one year to the other, even though those kinds of calculation, computing particle trajectory is very rare to have this on the exam. But it's important that you sort of play with that, that you're sure, okay, I understand the notations, I understand what is the variable, what is the function of. Yeah. In that same problem, we also discuss streamlines, which I barely discussed here. If you want to skip that problem entirely, completely fine. If you want to further really sort of get accustomed to the notation and everything, then do this problem. Right? But it's not a problem. Students always get stuck on this problem in the homework, and I'm like, okay, this is not something which is so important because it's going to be an exam question that you have to spend your whole life on. Right? So it's really for you to get used to the notations and the idea of what is a steady flow, what is an unsteady flow, what does this formula represent. So let me show you real quick particle trajectories, just that we all agree what these are. Okay, so here, those are my streamlines, those were snapshots. Okay, yes. My computer is slow to respond. The MATLAB is really, maybe I'm pressing too many times. Okay. All right, so here this is a particle, right? And this is the velocity field at any given time. And then as you advect, as time moves, the particle moves, and the particle is advected. Oh, this is annoying. The particle is advected with the flow. So at any given time here, right, you see that the particle is going to move in the direction of the local flow velocity at this given time. Yeah, at every given time, this is what happens here, right? Except, of course, the flow field changes, right? So if you now look at a later time, my particle is here. This is your particle trajectory. This is the physical trajectory that the particle has followed. But it is very clear that at this later time, your particle trajectory is, of course, not tangent to the velocity vector at this time, because in the meantime, the velocity field has changed. Yeah, is that clear? So you clearly see here that there's a distinction between your streamlines and your particle path lines. When the flow is unsteady, when the flow is steady, they're the same. Is that clear? That's one distinction, and this is the particle trajectory. Really, it is. Yeah. So here is just so that you see you have the particle, the streamline pattern. You see that your particle trajectory is clearly different than your streamline pattern. The streamline pattern changes. If you take a snapshot, the particle trajectory. Once you see a particle trajectory, you don't know exactly what the flow field was later on. The particle is just at one point. Okay, and then there's this last thing, which is called a streak line. And this, okay, I'll just explain you roughly what it is. Is this, this curve by all of these colored plots. So this here is, let's say, a streak line. Forget about the small lines here, but if you follow all of the dots here, right, this is going to be a streak line. And I'll tell you why it's important historically. You know that it used to be that you would do flow visualization by releasing dye from a given spot. Right? Or what you would do is you would just release hydrogen bubbles. Right? You would put a lot of, you put some electricity in something, you would generate the equation of hydrogen bubbles, and you just follow those hydrogen bubbles. They will all be released from one point. Yeah? And then, of course, you see a streak of hydrogen bubbles. If the flow is steady, then the streak of hydrogen bubbles represents the streamline. Right? But of course, if the flow is unsteady, then the streak of hydrogen bubbles do not represent a streamline. Right? And they don't even represent the particle path lines. What they represent is the curve that is drawn if you link all of the particles which were released from a given point at a given time. Is that clear? And that's different again from particle path lines. But historically, experimentalists have looked a lot at streak lines. And just here, in that case, we constantly released particles from this one point, right? So the blue one here is the particle that we released first. The red one is the particle that we released last. And in between, you see the location at a given time of all of the particles that we released. Of course, in between, the flow changed so much that some particles are going now underneath the cylinder, where other particles were sort of drawn to go above the cylinder. And that's what the streak line is. Then I'm not going to go into more details on that. Is that clear? Yeah? Any questions before we move on? Now it's the time. Are there any questions in the other rooms? No? No question? Yes, okay. True. They can. Yeah. So streamlines don't never cross. Why? Because that would mean that at a given time, right, you had a velocity field which was going, you had a velocity field in this direction at one point and a velocity in this direction at one point. That can't be. That's why they don't cross. The particle path lines, depending on what the flow is doing exactly, yes. But your particle trajectory, the line is not really so interesting because it's the history of where the particle went. Right? So if they cross, they don't necessarily, they wouldn't cross. If you went to the intersection, that intersection would not happen at the same time. It would be, okay, at time t, the particle was here, and at a later time t, another particle was there. That can happen. Yeah? Any other questions?
Yeah. Particle lines don't cross, but streamlines.
Streamlines don't cross. Yeah. Particle trajectories can, but it's not so important.
So streamlines are just multiple particles.
No, streamlines don't cross because if you think about, well, just think about this. If I had another streamline going like this, right, that would mean that at a given time, I would have particles going this way and that way, but it's not possible. Yeah, so they can't.
Then how is the origin of your vortex?
The flow is up there. You have a singularity. Yeah. All right, any other questions? No? All right, okay, so there are no further questions. We're going to move to the last thing that I want to discuss today, and that is the material derivative. So let me just zoom back to the roadmap here. Right, roadmap now we are doing 1.5, we're doing material derivatives. That is one more thing, which is another derivative. You know partial derivatives, you know straight derivatives. In fluid mechanics, understanding what the material derivative is it's helpful, and it's linked to what we've been discussing earlier today. All right, so let's do that. So this is 1.5. Material derivatives, and I'm just going to warn you that, for those of you that weren't too sure about their single and multivariable calculus, this is where having watched this video will help you follow. Okay, so I'll give you the formula directly, and then we'll discuss how you derive it. So here is the definition. Given a flow field u x t, so this is a velocity field. In principle, I'm not saying anything, so let's assume it is an unsteady flow. Right? Let's consider a scalar field, for example. And I'm going to call it psi. Right? But to make it more concrete, think, for instance, a scalar field that could be temperature, right? That could be density. This is temperature. This is density. Or it could be anything else. It could be the concentration of, I don't know, a particle chemical at this position, right? Or in space. Or it could be the concentration of pollution or any sort of dye or trace of which you're following. So it's a scalar field. It's a quantity which is defined on the flow field. It's a quantity which can be affected by the flow, or it can diffuse. But you're just interested in the value of this quantity. This quantity could be the pressure as well. It could be the velocity in the unidirectional stuff. I'm just using this as a generic quantity, just to help you. I think the easiest for you is to think about the temperature field, and so the material derivative is of psi divided with a capital D. Right? So psi here is defined as a function of, let me write that clear here. So when I write this, this is your position vector. this is time. Right? And you have full knowledge of psi. So your variables are independent. X, Y, Z, and T are independent. You may be interested in the temperature at this point at time 0, and you have also knowledge of the temperature at that point at time T1. Right? So they're fully independent. You have full knowledge of your field. The material derivative is equal to the partial of psi, partial T. Right? So here, this is really the partial. So what happens when I fix X and I change time, plus an operator which is called U, the U grad, so U dot the gradient of psi. Right, so this is here, I'm putting it right there, so that you already photograph it, and sort of see a little bit how it works. And that you will have to remember, we'll see that many times throughout the first quarter. All right, so before we go to that, we need to discuss two viewpoints, the Eulerian and the Lagrangian viewpoint, right? And this is all different viewpoints of how do you see motion inside of a continuum. And so that's important for us to discuss. So we'll start with the Eulerian point of view, because that's the one that is really related to how we define functions usually. Eulerian. That's the Eulerian viewpoint. Okay, so let's think about flow. Like that, let's say this is my flow. Again, the flow might be unsteady. But when you look at temperature, for example, you have an Eulerian viewpoint if you put a temperature probe at one location in the flow, right, and you record the temperature and the changes in temperature at the one place where your probe is. Right? That is, you have sort of an Eulerian viewpoint. You're looking at changes, but at a given place. Yeah? So this is what you have. So here I'm fixing a location. Let's say that is here my X naught. Right, this is X naught. The flow might be unsteady, right? But you have an Eulerian viewpoint. That means you look at the variation or the changes, in, I'm going to call psi, let's think about temperature at a fixed location. Okay. What that means though is, so say for example, you were thinking about concentration of pollution or something, or pollutant, yeah? That means that you're looking at the concentration at this time. Later on, you have another reading, but of course, the material that was around your probe has changed in between. Whatever was, the lead time, whatever was here at time t equals 1, has now moved here, and you're measuring the concentration of what replaced it. Yeah? So you're really not following what we call material elements. Is that clear? So when you're looking at that, then what kind of state changes do you look at? So here I have, for instance, if you were doing this experiment, then you would plot really psi at X naught, and X naught is a constant there, so given location as a function of t. So if you think about this guy here, this is here, let me write X equals X naught, maybe that will make it easier. You're plotting psi at X equals X naught as a function of t. This is time, and it may vary, go up and down. When you look at this variation, what mathematical quantities do you look at? You're looking, sorry? I'm asking in terms of the variation. So if you think about the variation, so for the Eulerian standpoint, the variations, if you look at the time variations, what quantity do you look at? You look at No, it is mathematics. If you want to describe those variations in temperature, you're writing some sort of derivative, right? The variations or changes are always represented by derivatives. What derivative do you write? Which d? Let's say those d's. It's a partial, because you're fixing x. The definition of a partial is the derivative when you fix all of the variable but one. And in that case, what you're doing, you're fixing all of the variables, you're fixing x, y, and z to get x naught, and you vary t, you let t vary. So it's a partial. The variation you're looking at are precisely the partial of, with respect to p, of phi, right? And sometimes what you say that you actually, just to make clear where you hold things constant, you're holding x constant at x naught, right? Or you could simply write it as the partial with respect to t of psi. Psi is a function of zero variables, right? Of x at x equals x naught and t. That's the quantity you look at. Is that clear? Yes, yes. Oh, depending. So of course, if now sometimes you may want to zoom out, right, and say, okay, psi. I can think of psi x naught t as a function of a single variable. In that case, I would give it another name in that case. And because here I introduced psi as, if you see here, you're introducing psi as a scalar fit. And here I'm clearly introducing psi as a function of 4 variables. Yeah? All right, so remember, when you see a partial respect in time, it's the Eulerian perspective. You're looking at the time changes when you're fixing the position. Yeah? Now, this is different from the Lagrangian point of view. Lagrangian viewpoint. All right. So the Lagrangian viewpoint is slightly different. And it's more related to what we just saw with particle trajectory, because we're following material elements. So let's think about this is flow. Again, I'm not telling you whether these are streamlines or particle path lines, but what you do is that you may have here a particle, and the particle is here at time t, right? So here, this here, x is the location of the particle at time t, yeah? But the same material elements, I'm following this material element, and let's say the flow is steady. I'm not saying the flow is unsteady. Let's say even if the flow, it doesn't matter if the flow is steady or unsteady, there's still a difference. So let's assume for you, let's fix it and say it is steady, right? That means that, let's say this is a streamline pattern. And that means that at a later time, my particle is going to travel along this streamline, and at a later time, it's going to be here. Yes? So this is my particle followed by streamline. It's now at a position x plus delta x at a time t plus delta t. So it moved, but it moved as following being affected by your velocity field. So it's a material element. This here, let me write, is a material element. So the value of psi was psi at xt here. And of course, the value of psi of your temperature at a later time now is psi at x plus delta x and at t plus delta t. Yeah? This is the value later on. Yeah? So if you look at these changes, if you look at the changes of your function as you follow the material, if you look at the changes of the material element, the changes in your field or in your psi, as you follow the material element, that is the Lagrangian perspective. Yeah? So the Lagrangian view, so the Lagrangian viewpoint, this is when you look at variation. And when I mean variation, again, I mean changes in time changes in time. look at variation or changes in time. When you follow a material element, variations of phi, following. So here you're not at a given time, at a given activity, you're following material element. Right? So when you adopting a Lagrangian point of view, what problem? Is what? Oh, can you ask them to tell them to maybe go back to the, or can one of you maybe sacrifice a few minutes of lecture and go to the front desk and say there's a problem? Yeah? No, thanks. All right. Okay, so this is the Lagrangian view. Yeah? And when you have a Lagrangian view, the reason why you need that is because in dynamics, usually everything is Lagrangian. When you say use the second law, you apply it to a material element. So you may want to know what's happening to that material element. You want to be following the signature. So in that case, those variations are represented by what we call the material derivative. So these variations, in this case, variations are represented by the material derivative. Okay? So that's the definition. Now, of course, going from the definition to the mathematical definition is a little bit tricky, so we'll do that now. Derivation. Hopefully, I'll be able to finish, but maybe not. So maybe you'll have a little bit of that on Thursday. So derivation. Okay, so to do the derivation again, you know what, and anyone unclear about what the material derivative is, just keep going, that's right. And the rest of them not. The definition is clear. Now you're looking at the changes at psi as you follow a material element. So the question that you're asking is how does psi change? How does psi change in time as we follow a material element? That's the question. Yeah? Now, when I write psi, we write psi as a function as a field, right? And here, when I'm writing it like that, of course, I'm assuming that psi is a function of 4 independent variables, which are your 3 position, x, y, z, and time. Yeah? So in principle, how do we write a change in psi? So you've seen that in the video. So one, a change in psi. And we call that delta psi. Where does that depend on? You write the total differential. A change in psi from a position x. I want to know how does psi change if I take a step delta x in the x direction, delta y in the y direction, delta z in the y in the z direction, and if I take a step delta t in time. So in principle, a change in psi. Anyone did not watch the videos on differentiation? This is where it's going to be the handles. So if you haven't, then do watch them. And if it's still unclear, then get back to me. But in principle, you'll see that if you want to know how psi changes locally, the changes in psi depend on, of course, which step you take in your 3 direction, between x, y, and z, and the step you took in time. That's your linear approximation for psi, if you want. And those coefficients here, by definition, are the partials. Right? Partial phi, partial t, partial phi, partial x, partial psi, partial y, and partial psi, partial z. And note here, this term here is will be the change in delta phi. So let me call it delta phi prime due to due to delta t, to the fact that I'm looking at the later time. This here is going to be the change in psi due to the fact that I took a step delta x along the x direction. Same here, this is going to be the delta psi, the contribution to the variation of psi due to the fact that I took a step delta y and y, and same for that. Yeah? Is that clear? That's just a definition of the total differential. Yes. Of course, here we took, when I'm writing this, I'm assuming I can take a step delta t, I can look at any time I want, and I can look at this position and see what the difference is between psi at this position and this one. Yes? But in reality, if you're looking at the material derivative, this is not independent, right? If I'm here and I'm interested in psi, I cannot say I want to look at the variation between this location and that location. My variables are no longer independent. Once I say I'm following this particular particle, right? Once I'm saying I'm following this particle is moving in this direction. X, Y, and Z are no longer independent variables. They're all functions of time. Is that clear? Because you have to follow a particle trajectory. So to derive the material derivative, for the material derivative, so this is for the Lagrangian viewpoint, X, Y, Z are not independent on time. Yeah? We want to characterize the delta psi, as a contrary, what we want to characterize delta psi as we follow the material element. Right? So clearly the position is not independent on time. Right? So here's the question. I think we're going to have to start with that. I don't know if I'll be able to finish, but so how are delta x, delta y, and delta z related to time, so to delta t, in this Lagrangian when we follow a material element? When we follow a material element. So if we go back to this picture, I'm opening it up to you. So here you have this material particle, right? And you consider it as a material element, so you're following it along its trajectory, right? So you're forced to move along this direction. It's clear that your delta x is no longer an independent variable. It's not independent from your time. I cannot say, no, I'm going to move it. No, you can't move this way. You have to follow that. So how is your delta x related to your delta t? We just discussed that before. Anyone else? Yes? Through your local velocity field. Of course, yeah, this is the trivial answer is through your velocity field. If you think about delta x and you follow the material, then what is delta x equal to? Yes? Yeah, so u, which is the component, so here my velocity vector, my flow field has three components, which are u, v, w. Right? So it's the component of the velocity in the x directions times delta t. Yeah? Same for delta y. Delta y is equal to v times delta t, and delta z is equal to w delta t. Yeah? So here the question is, how are these No, the answer is through the velocity field. That's what one of you said, through the velocity field. Is that clear? Any questions on that? No? All right, so then I'll take 1 more minute of your time. Then you'll see that this delta t, delta x, so delta x, delta y, delta z are no longer independent. So they are u. This is here is u delta t. This here is v delta t. This is w delta t. You see that? You can factorize the delta t's. You have delta t's everywhere, and you wind up with delta psi. Your change as you follow the trajectory is equal to partial psi partial t plus u partial psi partial x plus v partial psi partial y plus w partial psi partial z, all of that times delta t. Yeah, and this here, you see that, right? This is how you relate a change of psi to a change of delta t as you follow your particle and material element. So this is called the material derivative. That here is d psi dt. And so I can write it, so d psi dt, your material derivative, is equal to partial psi partial t plus u partial psi partial x plus v times partial psi partial y plus w times partial psi partial z. My z's look like my t's. This is not good. This is the material derivative. Yes? Is that clear to all of you? That's how you get to that one. So this number, when you see this number here, you know that what you're representing is how your function psi changes in time, but not at a given location, but how it changes if you are following a material element. Yeah? So if you're moving with the local velocity field. Yes? All right, I think we're right on time today. So I'll see you on Thursday, or in office hours tomorrow if you have questions.
It's the same, right?
Yeah, it's the same. Yeah.
In this question, the airflow in lungs,
Yes.
I found out 3 parameters. One is the geometrical parameter, which is basically d by n.
The diameter, yes. Okay,
Yes. Another is a parameter with the frequency, and which is proportional to some other quantities, the 3 of the parameters. And another, I just found out the Reynolds number. I think that's not needed. So
yeah. So the Reynolds number, yeah.
how do I arrive at this conclusion? Like, what do they represent?
What do they represent? Just tell me what do they represent.
It was a quantity like f, I think f rho square, f rho p, and L, depending on the flow density.
I mean, one should include the time scale.
So yeah, one included f, yeah, frequency.
Yeah. So what would that represent?
I couldn't figure that one out because
I like studying.
Think a little bit longer then. In that, which other quantities do you have?
I think it's f, p, rho, and L.
You have f. Yeah, what else?
I have del p. I have rho. Yeah.
No, forget about that. No, f should include something else.
And I'll think about it a little bit longer.
Yeah, actually, delta p is not. Is it?
Yeah, there's delta p. Yeah, delta p now.
Don't mind. Don't.
Yeah, I mean, delta P, you can always. Yeah, no, you want something else. In the because of course, yeah, you have some seconds in delta P, but that's not no. Let me you want viscosity. In your non-dimensionalizing of you can also put in the way you want to think about it. You want to put the viscosity in your non-dimensional group related to the frequency. Right? And then think about what that represents.
Okay.
Yeah, and if you don't know, we'll see it later in the class.
And I still couldn't figure out the Olympic rowing thing with the number of
So
rows.
all right, so what I told you, the important thing is at some point you have to think about the horizontal motion of the boat.
Yeah.
Right? So you have to think about some quantity, right, where you think, okay, the more I increase, I mean, you could say, okay, let me see. I increase the number of rowers, right? So from 1 to 2 to 3 to 4, my velocity linearly increase.
Yeah.
Do you think that would make sense? Do you expect that? You could, huh? You can say, okay, let me say physically, I feel like the more people, linearly, the velocity is going to increase.
Yeah.
Would that make physical sense to you?
Yeah, somewhat, yeah.
Would that make physical sense to you?
Velocity.
Huh?
In a certain way, but if you look at the drag, it's velocity squared, so
It's half.
I mean, look, for instance, just think, if you are on a boat and you're rowing, huh? you are there, right? And you add me, and then it's the same as what you do. Your intuition tells you we'll go twice as fast.
Intuition, yes, but
Yes.
yeah, because the
You have
force.
bad intuition. Oh, think now. So you put 10. Do you think it will go 10 times faster?
No. Okay, I get what you're saying. Okay.
Like, let's put it that way. All right. So you're dragging something. You're dragging something. You know, I help you out. Or you put 3, 4, 5, 6, 7. You feel like if you add now 10, you're gonna 10 times faster. Not necessarily. Think about what you've seen. What you've seen in the Olympic Games. Do you feel like the boat goes like 10 times? The boat with 8 people goes 8 times faster than the boat with 1?
No, because the mass is also increasing.
Huh? And if you put like 100 people in there, do you think it would go?
No, it won't, because the mass is also increasing.
Yeah, it won't. You feel like it won't. So what quantity? Because at some point, that's what you want to. You want to somehow in your experience say, okay, the more people, in terms of how it's going to move, the more what? So if you increase the number of people,
the mass is increasing.
Yes, but the mass is going to be a force balance in the y direction. But if you think about the x direction, the more people you add, what physical quantity do you think is going to be more? I put 2, I have twice more of what? If I put 4, I have 4 times more of what?
Force.
Huh?
The force increases. Force applied increases.
Yeah. So you think if you increase by 2, then you have twice more force.
Yes.
Right? If you increase by 5, you have 5 more force. Yeah. You can try, and you'll see what you get.
I don't think the force will increase. I mean, 2 people have twice the force, but the drag will also increase.
Are you sure 2 people have twice the force? Why should it? Which physical principle you want to do? Think about that. You can definitely try. I mean, there's no right and wrong answer. Eventually, you'll compare with experimental data. That's going to tell you whether you have the right approximation or not.
If you put a motor in the boat, you put 2 motors in it, it's going to have twice the force. Then the force.
Do you think it's really the force of the atom? So actually, it's a very good point. Very good point. Now, hold on and think usually if you characterize the boat, what is the quantity character? It's the same with the car.
Excuse me for 2 seconds. I assume you don't need the streaming anymore, right?
No.
Yeah. I'm going to turn you off upstairs.
Yeah. You have if you identify that, you have your answer. Even your engine, right? Your engine, if you characterize the people on your engine, yeah? Does it tell you engine 200 kilometers per hour? Does it give you the velocity?
No.
No. Does it give you the force? It gives you something in newtons. It will give you the power.
Okay.
Yeah.
Yeah,
You can be
so far,
sure
yeah.
if you add 2 people,
Yeah.
they're gonna have twice the power.
Using the power.
But you should try and see, because you'll get different scalings if you do force. If you do velocity, it's based on nothing. Velocity is based on no physical principle. Forces, I know every single the first thing about a force, but actually the net force you impose is very much a function also of what you are pushing against. Right? You don't work at constant force. Right? Because if you're not pushing against anything, then yeah. But you work, usually you can be pretty much sure if they're all doing their best, you'll have a linear function of the power input. And they all put the same power. That is pretty much sure. They will all have burned the same amount of calories roughly speaking. Yeah, they're doing their best.
Yeah.
That's the bit that you should put linear to end. Yeah.
Okay. Another question.
Yes.
It's totally unrelated to the materials course, but I saw the course are not videotape.
Oh, they're not. Okay, let me just do stop share actually.
I get the one I was thinking.